Welcome my friends, welcome to my next lecture. Now this lecture, my plan is to talk about an example of vector surfaces integral that I already discussed in my last lecture. Of course, one example I have discussed, couple of more examples I will discuss with some properties, then I will stop here. So that's how I will finish this portion, surface integrals. In my next lecture, I will talk about what is called new topic, that is called Green's theorem, Stokes theorem and divergence theorem. So my plan for today's lecture is this lecture at least to talk about more examples for vector surfaces integral. Okay, so as I promised that I should start with few more examples, like in my last lecture I talked about the notions of vector surfaces integral, and if you remember how I define vector surfaces integral, for vector surfaces integral I started with a smooth surface with the orientations, and then I started with a vector field, then I introduced the notions of vector surfaces integral of my vector field capital F over my smooth surfaces S in terms of the scalar surfaces integral. So since I am starting with a oriented surface, I will have the unit normal vector at the point pointing outward at each point. So what I am doing, actually I am having this vector field capital F, then I am taking the dot product with that unit normal pointing outward, then making a functions which is called scalar valued functions, and then I define my vector surface integral as the scalar surfaces integral of my functions f dot n cap, that is sometimes called the normal component of my vector field capital F over my smooth surfaces. And once I have that one, then this is same as I can write it as, if you remember, for the scalar surfaces integral, that can be written in terms of double integral if I know my parameterizations of my smooth surfaces S. And if I suppose my parameterization is small phi with parameterizations variable u comma b, then the corresponding vector surfaces integral of my functions capital F over smooth surfaces S, which is nothing but the double integral over R. R is the domain of my parameterizations phi, double integral over R capital F of phi uv, if you remember, if my phi is a parameterizations, u and v are parameterization variable, dot product with phi u cross phi b. This is another vector. So you take the dot product and you just perform this, make a scalar and compute the double integral over this region. That means double integral over R capital F of phi of uv dot product phi u cross phi b times du dv. You have to perform that double integral. Okay, so just recall that one. So if you remember, if you forgot the formula, this is the formula. So if I have a vector field capital F with the orientation is n cap, so that means what you do, you just vector surfaces integral, that means that integration over S capital F d S cap, which is nothing but the scalar surfaces integral of this function f dot n cap over smooth surfaces S, and that is nothing but if my smooth surface S has a parameterization is phi, that means it is capital F of phi ub dot product phi u cross phi b over the region. This is nothing but the domain of my parameterizations phi times du dv. Okay. So one example I discussed. Now I will start with another example. So this is one. So suppose this is my vector field capital F, which is x comma y comma z, which is z comma y comma x. So evaluate the flux integral. Sometimes I will not say that okay, calculate the vector surface integral, rather I will say that okay, calculate the flux integral. That means you have to perform the vector surfaces integral of your vector field capital F over the smooth surfaces. So that's how I have written. So evaluate the flux integral, that is nothing but this integral over the unit sphere S x square plus y square plus z square is equal to 1. That means it's a unit sphere, right? And what is this integral? This is nothing but the vector surfaces integral S of my vector field, and that I denote it as this. So sometimes I will say that calculate the vector surface integral, or sometimes I will say that okay, calculate the flux integral. So what you do? Again the same step. Once you have the smooth surfaces, first you get the parameterizations. Now it is a sphere of radius 1 and you know the spherical coordinate system, so you know the parameterizations. So what is my parameterization here? This is nothing but capital R I am denoting is the parameterizations, capital R of u comma b, and this is nothing but a times, now a is 1, so that means this is sin u cos b, sin u sin v, and cosine of u. U runs from 0 to pi, v runs from 0 to 2 pi. Now this will give you a full sphere kind of sphere, because u runs from 0 to pi, not 0 to pi by 2. Earlier some example I have discussed 0 to pi by 2, that means a portion of the sphere. So therefore since u runs from 0 to pi and v runs from 0 to 2 pi, it is nothing but it will give the full sphere of unit radius. This is the corresponding spherical coordinate system of my sphere, that means this is the corresponding parameterizations with parameterizations variable uv. Then how to calculate it? You just get the vector ru, or that means del r del u, and del r del u take the cross product, and of course this is your R of u v functions. What is del R del u? That means this is nothing but minus cos u cos b minus cos u sin b, then minus of sin u. This is the Ru vector, and what is Rb? So Rb, so maybe you can just write it. So I am just writing it. So del R del u, which is nothing but Ru at the point u v, which is nothing but with respect to u. So that means this is cos u cos b, then cos u sin b, and this is minus sin u. This is one vector, and del R del v, if I calculate, this is R v at the point u comma v, which is nothing but, so with respect to v variable, that means this should be minus sin u sin v, then you have a sin u cosine of v, and then 0, because I am going to take the derivative with respect to v variable, but this is independent of v, that means this is 0. So that means this should be minus sin u sin b, sin u cos b, and so now I have two vectors Ru Rb. You just take the cross product and it will end up with this kind of vector. First component is sin square u cosine b, second component is sin square u sin b, and third component is sin u cos u. So now you have the vector Ru cross Rb. So now my corresponding flux integral or vector surface integral of my capital F over smooth surfaces is, which is nothing but the scalar surface integral of the normal component of my capital F, that means like f dot n cap over s, and if we just change it to the corresponding formula, then it should be actually what? So f of capital F of phi of u comma v dot product with, I think this R na, so you can write it as, so capital F of R of u comma v dot product with Ru cross Rv times du dv, and the corresponding region is R, which is nothing but this is the region, that means 0 to pi, this you can write 0 to pi cross 0 to 2 pi, that is it. So therefore this is the one. So 0 to pi, 0 to 2 pi, this is the corresponding integrand, that means this is the object. If you calculate it, you will get it, and du dv you have to perform that integral. Now this is very nice, it is a separation of variable, you just perform the normal integrations, and if you do that, it turns out that the value of this vector surface integral or the flux integral is 4 pi divided by 3. Okay? So that is the process, or that is the formula, that is the way, these are the steps. If you follow, you will be able to calculate what is your vector surfaces integral or the flux integral. One more example, okay. So like I am saying that, okay, surface over the xz plane. So okay, if I have this example. So now look, I will ask this kind of questions. Find the outward flux of my vector field capital F through the parabolic cylinder y is equal to x square, where x running from 0 to 1 and z running from 0 to 4. So that means find the outward flux. So that means it clears from the context. If I ask this kind of questions, that means you have to somehow calculate the vector surfaces integral of my vector field capital F over this parabolic cylinder that I have written over these surfaces. That means parabolic cylinder y is equal to x square, or x running from 0 to 1 and z running from 0 to 4. That means you have to calculate the vector surface integral over this surface. That means first you get the parameterization of this surface, and your vector field is given. You calculate the corresponding phi u cross phi b, whatever that vector, depending on what parameterization and what parameterization variable I am talking about, and then make it to a double integral and calculate it. Okay, so look, step 1. Step 1 is writing the parametric equations of your smooth surface S, which is nothing but the parabolic cylinder y is equal to x square, x running from 0 to 1 and z running from 0 to 4. What is this? If I calculate the parameterization, so parameterizations of my smooth surfaces S, which is nothing but phi of xz. So of course y is equal to x square, then its first component is x, second component is x square, and z as it is. So this is the corresponding my parameterizations of my surfaces, where x comma z runs over R. And what is my R? It is a very nice domain in R2, x runs from 0 to 1 and z runs from 0 to 4. Okay, so that means it is a kind of not square, it is a kind of rectangular region in R, in R2, which I denote it as R, and this is the corresponding parameterizations phi with my parameterization variable x and z. Now once I have my parameterization, then you just calculate del phi del x and del phi del z, take the cross product, get the vector, and calculate the double integral as I said. Okay, so what is my phi x? Because phi is very nice, so it should be 1 comma 2x comma 0, phi z, that means this is independent of z, so therefore this is 0 0 1. So this is the vector, this is the formula I cap j cap k cap. This is the first component of phi x, that means 1 comma 2x comma 0. Third one is 0 0 1. If you do the formula, that means this is nothing but the vector 2x times I cap minus j cap. Then what is my vector? That means the vector is nothing but 2x minus 1 0. This is the vector. So now I have the vector phi x cross phi z, and I know my parameterizations, I know my domain of my parameterization. So now you have to just calculate the double integral, right? So what you do? So therefore this is my step 3, evaluations of vector surfaces integral, which is nothing but this is my notations, which is nothing but the scalar surfaces integral of my vector f dot n cap or the normal component of my vector field capital F over smooth surfaces. Now I can make it to a double integral. What is that? Integral over the region R in R2 capital F of phi xz. This is a dot product, I should write this is a dot product by meaning, because by looking at this object, that means this one vector I have another vector, of course by default it is the dot product, and dx dz, that's the double integral you have to do. Now this capital F of phi xz, you can easily do that. What is my capital F? So your capital F of xyz, what is this? This is actually yz comma x comma minus z square, right? And what is your phi? Phi is x comma z, which is nothing but x comma x square comma z. So what is capital F of phi of xyz? If I do that, it turns out that it should be phi of xyz, that means it should be capital F of what? X comma x square comma z, and which is nothing but, the first one should be yz. So yz, that means x squared z, right? Let's see, x square z, it is yz, it should be yz, right? Y comma z, so that means first component, if xyz goes to yz, right? So that means it is phi of x comma z, x squared z, yz means x squared z. Yes, I think that is correct. What about the second one, x as it is, that means this should be x, and what about the minus z square, that means this should be minus z square. Is it the case? I am getting. So look, so x minus z square, why I am writing this is y times z, I think. Oh, later I will put it at y is equal to. So this is perfectly all right. So this is the corresponding f composed phi of xyz, which is nothing but this one. So what I have done actually, I just keep as it is, right? I keep in terms of y, right? So that means f of phi of xz, which is nothing but the way capital F is defined, yz x and z square. I have written like that. So yz x comma minus z square, and this is 2x minus 1, that are already there, 2x minus 1, and k component is 0. Take the dot product. So if I take the dot product, which is nothing but 2xyz minus x times dz dx, but this time y is equal to x square, I know this is the one already given, y is equal to x square. If I do that, so it turns out that this is nothing but, you have to perform this integral, which is the integrand is 2 times x qz minus x dz dx, and of course z running from 0 to 4, x running from 0 to 1, and that's how the parameterization is given. X running from 0 to 1, z runs from 0 to 4. You do that, and you just, again it is a separation of variable. You perform what is called, first you have to integrate, okay, not exactly the separation of variable, it is a separation of variable, it is a separation. You make it in two integral, na? So what you have to do, x from 0 to 1, z from 0 to 4. So one is 2 x cube z dz dx, this is one, and another one is x from 0 to 1, z from 0 to 4, and then you have minus x dz dx. Now separation of variable, na? So what you have to do? So first you have to integrate with respect to z dz, and then you have to integrate with respect to x 2x cube. Similarly here, first you integrate with respect to z. Z means what? Constant function 1. You have to integrate 1 with respect to dz and x. So it's separation of variable. You can easily do that. If you do that, it boils down to that. This is nothing but changes to the corresponding x integral, and if you do that, this is nothing but 2. Okay. So I think that's how one can prove. So I think these two examples I have discussed. There are many examples are there. If you just go through any standard books or whatever, some books I have given the references. If you go through that books, so this is one of the way to calculate what is called vector surfaces integral. Okay, so more example you should try, if you calculate, then it will be more clear. So main part is that if I want to say that calculate the either flux of the integral or the total flux over through the surface, whatever it is, that means somehow you have to identify what is your scalar field and what is your smooth surface, and you have to calculate what is called vector surfaces integral. And now vector surfaces integral, you can define it in terms of what is called scalar surfaces integral. That means by computing the normal component of F. That means if I have a surface S, smooth surface with the unit normal pointing outward, then you get the normal component, and you have to calculate the scalar surfaces integral. Now whatever, either whether I want to calculate the vector surface integral or scalar surface integral, main part is that given the surface S, which is nice smooth surface, first you have to get the parameterization. So that is the main hardest part. Once I have the parameterizations of my smooth surfaces S, rest of the part is the calculations, because you know how to calculate or what will be the corresponding formula for scalar surfaces integral or vector surfaces integral. So first, if I give or if I say that calculate this vector surfaces integral or scalar surfaces integral, so you have to first get the parameterizations of your smooth surface S, and once I have the parameterizations phi with parameterization variable u and v, and suppose the domain of my parameterization is very nice, then you have to just perform a double integral, that is it. So, that means you have to calculate a double integral, of course with an appropriate changes of your kind of integrations. That means if I want to calculate the vector surface integral of my vector field capital F over S, so there is a formula. What is the corresponding formula? This is nothing but integration over R. R is the domain of my parameterizations. Then you have to do capital F of phi u b dot product with phi u cross phi b du dp. So, that's what. And if I have only scalar surfaces integral, the same thing, like F of phi of u comma b, then norm of phi u cross phi b, and then du db. So, you know that what the calculate the scalar surface integral in terms of double integral, similarly vector surfaces integral in terms of double integral. So, major part is that given the smooth surface, you first try to get what will be the parameterizations of my surface. Once you have the parameterization of surfaces, rest of the part you can easily do that. So, that is the process, and that is how one can calculate the vector surfaces integral. Okay, I think I should stop here. So, I have discussed in a couple of last 1 or 2 or 3 lectures the notions of surfaces, smooth surfaces, oriented surfaces, and notions of what is called scalar surfaces integral and vector surfaces integral, and couple of examples I have discussed, and some physical significance I have discussed. So, I think I should stop here. In my next lecture, I will start with what is called Gauss theorem, Green's theorem, and Stokes theorem or divergence theorem. So, these are the few kind of concepts are left, and that I will start with in my next lecture. I think I should stop here. Thank you.